In the previous video, we've had a look at this expression here, which is Ampere's circuit law. And now let us just try to simplify this expression and make more sense of it. So let me just remove the name of the law. Now, how do I first of all remove this integral sign, because this seems very dangerous and this makes it I think difficult to really digest and understand. So how do I remove this integral sign? Well, first of all, what I can do is, if I have one simple straight wire like this one, I know that if I take a loop, so I'll just keep it like that. If I take a loop around it, so if the loop is circular, this loop that is represented by the tape, if this is circular, as in this case, and the loop and this wire passes through the center of the loop, then I hope you can imagine that the magnetic field at all points along this loop will be constant, right? Because the distance of every point on this loop is the same from the wire. So right, so this is what I'm trying to show you, the distance from all points. So if this is the case, you have the current carrying conductor in the middle and you have the loop around it. So if the current carrying conductor passes through the exact center of this loop, every point on this loop is equally away or is at an equal distance from the wire, and therefore the magnetic field at all points along this loop is equal or constant, and then the magnetic field simply becomes a constant, and I can simply take that total magnetic field out of the integral sign, and what I'm left with is I can just write the B outside. This is the total net B along the whole loop, and I'm only left with the closed loop integral of dl. And what is the integral of dl? Well, integral simply means the summation or the sum of. So what is the sum of all the small dl, or all the small pieces that I was using? Well, the small pieces are of this whole loop, and so if we add all the pieces, we should get back the loop, right? So if we add all these dls, we get the length of this loop. So I'll just replace that by a large capital L. Let me bring it closer. So I had a B there, and I can replace the small dl with an L, because L here is the total length of this loop, because if I add all the small dls that I have, if I add them, I should get the length of the whole loop, which is represented by the capital letter L. So this is what I'm left with, and I hope this seems simpler. And one thing to note here is that I can do this only in cases when I have such kind of loop where the magnetic field at all points is constant, so that I can take it out of the loop and simplify it. If it is not constant, you'll have obviously have to integrate, and it will be a tedious task which we'll not get into at this moment. Now I hope that makes sense. And yeah, if this is a circle, as in this case, we can further simplify it by just taking the radius of the circle as r. So if I take the radius of the circle as r, I know that the circumference of the circle would be 2 pi r. So instead of writing L there, this length, which is the circumference, would become 2 pi r. So B times 2 pi r, and to solve for B, I can simply shift this 2 pi r to the other side. So I'll rewrite the whole thing. B equals mu naught I upon 2 pi r, and yeah, that's it. The magnetic field, the total magnetic field along the loop around this current carrying conductor would be simply given by mu naught I upon 2 pi r. Now everything makes sense here, I hope. B makes sense, 2 pi r makes sense, mu naught also makes kind of sense, but what exactly is I? Now initially that also makes sense. I is the current in this wire, but what if we have multiple wires? What if I have this wire here, and let's say I have another wire here? Now what happens? Now which current do I take? Do I add both the currents? What do I do? Well, Mr. Ampere here, he's given us some clue here. So what he tells us to do is attach a surface to this closed loop. So this is a closed loop. I need to attach a surface to the loop so that I can measure the current through that loop, through that surface. So what I do is, let me take a bowl here. So I have this bowl here. This bowl is obviously a surface, a curved surface, but that doesn't matter. He just asked me to take a surface. So yeah, this is a surface, and if I attach this surface to this loop here, just like that, so now I have attached the surface to the loop, right? Now what he tells you to do is, now he tells me that if you have to find the total magnetic field along this circular loop, that will be equal to mu naught I upon 2 pi r, where I is the current, net current to be precise, through this surface. Now Mr. Ampere has done a bit of show off here. He has said that it's not necessary for you to take a flat surface. You can take whatever kind of a surface you want, as far as it just connects with the loop in this manner. So it should not be open, it should be a closed surface from one side, and it should with its mouth as the circular loop. So I hope you understand. It should be this kind of loop. It can protrude out like this, so it does not have to be a flat surface. It can be a curved surface like this, but it has to be attached to a loop in this manner. And now he says that find the net current through this surface here. So the net current going through this surface, that is this I here. Now you might be confused as to why he did such a weird why did he define I in such a weird way. Now, so let me just make that thing just a bit more sensible to you. Here I have a plastic bag. So this is also a surface. Now I can take the loop here and attach the plastic bag in this manner. So if I just fold it right, see, there you go. Now I have attached the plastic bag's mouth to my closed loop. So I have this closed surface which is attached to my closed loop, and there's only one way to get into this bag, which is here through this loop. Now he says the net current through this whole surface is this I. So what is the way in which I can get net current? Well, I can have the wire going in from here, and for it to complete the circuit, for it to be connected to this end back, it will obviously have to pierce through the surface, just like this. It has to pierce through the surface. I'll just keep my loop for a moment. It has to pierce through this loop, and only then can it travel back to the other end and form a closed circuit, and so that current can flow through this wire. In case somebody tries to be over smart and he says, no, I will do something else. I'll take a bent wire like that, and now I'll put it through the opening of the bag, and now I have some current going in. So now I have some current going in through my, so this was my closed loop there, right? Now somebody can be over smart and tell me that this is my loop. Here I have some net current going in through the loop, but this net current does not pass through the surface. Won't this be counted? Well, you would be not very right if you say so. Why? Because the net current going in through the loop is equal to the net current coming out of the loop. So some current must be going in through this wire, let's let that be I, but obviously that current would go in, loop back, and come out from here to the remaining part of the circuit. And so I amount of current goes in through that section of the wire, and I amount of current comes out of the wire through this end. So the net current through this surface is I minus I, which is 0, because this I goes in and this much I comes out. So the net current is still 0, and so the magnetic field generated by this current would be in one direction, and the magnetic field generated by the other current that is coming out would be generated in the opposite direction, and the two magnetic fields would simply cancel out each other's effect, and the net field along this whole loop would again be 0. So that is why Ampere's circuit law is such a smart thing. In order for you to have some net current going through this surface, you have to take your wire, go in, and you have to pierce through this surface like that, and only then can you complete the circuit, and some net current can flow through this closed loop, and that current is the I here. So I hope that begins to make some sense to you. And one more thing to be added here is that I can have as big as a surface as I want. So this need not be as big as this bag, it can be as big as the earth itself, unless the opening is attached to this closed loop and there is no other open surface in the whole bag. I can take any surface and it would work pretty much fine. So that is Ampere's law, and yeah, those were the things that you need to know. But when it comes to the numerical part of it, this is the main expression that you need to keep in mind. In case of a circular loop being taken around a current carrying conductor, where the magnetic field along the whole circular loop is constant at all points, and the magnetic field would be given by this expression. And just to tell you, the magnetic field at all points along this loop would be obviously tangential, as happens with most other quantities. It will be tangential at every point, the magnetic field along this whole loop, and the magnetic field depends only on the distance from the current carrying conductor and the current in the wire. The rest everything else is constant for a given medium. Now lastly, if somebody wants to find the direction of the magnetic field, what we can do is we can apply the famous right hand rule. So let's say this is the wire here. What I need to do is I need to point my thumb in the direction of the current in this wire. So let's say the current in this wire is in this direction, so I point my thumb in that direction, and the direction in which my fingers curl, that would be the direction in which the magnetic field is present around this wire. So in this case, the magnetic field will be in this direction, right? If you look at from this view, if the current is going upwards, the magnetic field will be this way, anti-clockwise, and it will be concentric circles around the current carrying conductor. And yeah, that is what Ampere's circuit law is all about. That is it for this video.